solve for the equilibrium constant, Kc. Let's take a look here. We're given a generic equation. Half mole of X is placed into a system with a volume, so we got a molar concentration. This is an initial. We're going to use an ice box to figure out what the concentrations of all of this stuff, X, Y, and Z, are at equilibrium, because that's what we need in order to use the equilibrium expression. Okay, so I'm going to kind of just line it up here. I stands for initial, C is the change, and E is the concentration at equilibrium. All right, so let's see where these numbers go. Half a mole of X placed in the system, X, so we'll put that right here, 0.500 moles per, it's not 1 liter, so it's 0.750 liters. And we can actually do the conversion before. Why don't we do that? I want to turn this into moles per liter, or molar concentration. So 0.5 divided by 0.70, that's going to be 0.667 molar. So I'm just going to use that number, 0.6667 molar. So we took care of that number. At equilibrium, the amount of X is known to be, all right, so we're also given equilibrium concentration of X. So it's going to go right down here, right below it. All right, so I'm going to convert this to in the molar as well. So 0.350 moles per. The container is not 1 liter. Would have been nice if it was. So 0.350 divided by 0.74667 molar. All right, so we're going to end up with 0.4667 moles per liter. That makes sense because this stuff is getting used up. Now we can figure out the rest of the stuff. All right, using the coefficients here, this is going to get used up. X is the only reactant, so it's going to get used up. I'll use a negative sign for that. It's a little confusing. I'm using X, but that's X too. So let me use a different variable. Let's just call this A. Now that stuff's getting used up, right? 2x, 2a, so used to use an x. All right, and then this stuff is going to be made. All right, and then the z is going to be made 4 times the change. I'm just using these molar coefficients. And initially, there's going to be no products. So let's solve for a. Let's see what the change is. The initial is 0.667 plus the change, which is negative, so that's negative 2a, is going to equal the final condition at equilibrium, which is 0.667. Now we're solving for a, so we're going to subtract 0.667, both sides, 0.667. Okay, now we'll get rid of that. No more room. So now we have negative 2a is equal to negative 0.2003. Divide both sides by negative 2. Cancel that. Whoops, not the a. All right, so divided by 2, negative 2. All right, so a is going to equal 0.1002 if we want to take it out that far. So let's plug that in here. 1002. 1002. So we're going to get this number right there. Right, that's 3 times 0.1002, right? Because that's 3 times a, 0.3005. All right, then 4 times a, 0.4006. All right, I'm using my stored answers. We got all of this stuff. That's the whole point of that. Now we can plug that into the equilibrium expression. Just plug and place. I guess I didn't write it. All right, so let's write the equilibrium expression using the balanced equation. Oh, I need some more room. I'm just going to copy this over here. There we go. Whereas to solve for Kc, I'll just write this out here. And then 3.3005 cubed times 0.4006 to the 4667 squared. 0.00321. And we're going to use scientific notation. That's going to be 3.21 times 10, 1, 2, 3. To the right is -3.